Hey guys, this video is on chemical bonding. So we're going to start out with the octet rule, and this is what the octet rule says. It says that atoms gain, lose, or share valence electrons in order to have the same number of electrons as the nearest noble gas. And when I say nearest, I mean the closest on the periodic table in atomic number. The octet rule actually explains a lot of chemistry. It's a pretty powerful thing. As a simple example, bromine, a neutral bromine atom has 7 valence electrons. The nearest noble gas is krypton, and so in any chemical reaction, bromine is going to tend to do whatever it can to gain an extra electron so that it has the same number of electrons, or valence electrons, same thing as krypton, 8 valence electrons, which is why the bromide ion is always seen with a -1 charge, for example. There are exceptions to the octet rule, and you should definitely memorize these because they pop up. Beryllium, it ends up being satisfied with only 4 valence electrons. Don't try to put more. Boron with 6, aluminum also 6. Now, we're talking about molecular compounds here mostly, but add aluminum in there. Also, if there is an odd number of electrons in the molecule, so if you add up all the electrons, or the valence electrons, and you get an odd number, then that's going to be what we call a free radical. That means there's going to be one of those electrons that's not paired up, that's in an orbital and it's not paired up. Those are really pretty reactive compounds, but they do exist, and because there's an odd number of electrons, there's going to be some atom in there that does not have the octet rule satisfied. And then this is a big one, this last one here, expanded octets. It ends up that any element in the 3rd row or lower in the periodic table can have more than 8 valence electrons. So keep that in mind. We're going to use these exceptions later on in this talk. So now we're going to look at ionic bonds, which is how ionic compounds form, and then we're going to look a little bit at covalent bonds, which is how molecular compounds form. So ionic compounds consist of ions, a cation and an anion. We know this from the nomenclature. And the reason that ionic compounds form and what holds them together is that they're trying to get to their lowest energy, the most stable state. And you can describe this using what's called Coulomb's law. Coulomb's law says that the energy of interaction, E, between any 2 charged particles is equal to this number, and the units are joules, Newton meters, times the charge on the first particle, Q1, times the charge on the second particle, Q2, divided by the distance between the 2 particles. Now with these units here, guys, all the basically units in here are taken out. The R is going to be in nanometers so that it cancels here, and these Q's are just the integral charges, +1, -1, +2, -2 that we put on the different ions. For example, for calcium chloride, it ends up that the distance between the calcium ions and the chloride ions is about 0.267, twice 0.267 meters. The radius is about 0.267 nanometers. And so if we plug that in for R, the calcium's charge is +2, chloride ion's charge on the single chloride ion is -1. So when we put it in here, we get -1.73 times 10 to the -18th joules. That negative sign there, guys, means that it's more stable for those ions to be close to each other than it is for them to be far apart. And that's why they stick together, and that's how the ionic bonds and ionic compounds form. So atoms form ionic compounds so as to satisfy the octet rule. So they have the same electron configuration or number of electrons as the nearest noble gas. For example, if you take some calcium and some sulfur and you put them together, calcium, the easiest way it can gain a noble gas electron configuration, because its electron configuration is argon 4s2, is to lose these 2 electrons. When it does, it'll have the same electron configuration as argon. Sulfur, on the other hand, its electron configuration is neon 3s2 3p4. The easiest thing it can do to gain a noble gas electron configuration is to gain 2 electrons in these p orbitals and then be like argon. So if you bring these 2 together, they're going in the same direction. Calcium wants to get rid of 2 electrons, sulfur needs to gain 2 electrons. So they transfer electrons, and we end up with the calcium ion, whose electron configuration now is the same as argon, neon 3s2 3p6, and the sulfide ion, whose electron configuration is the same as argon, neon 3s2 3p6. It just so happens that they're both like argon. They don't have to be, just noble gas. So that's how ionic compounds form, and why they form too. Now when we form, in these ionic compounds, guys, the cations and the anions, we can, it's going to be relevant, you'll see in the next video, to be able to predict their relative sizes. And what we can say is this is always true, guys. When you form a cation, that cation is always smaller than the parent atom that it came from. So sodium, the sodium ion with a +1 charge, is smaller than just neutral sodium. Likewise, anions are always larger than their parent ion. So the oxide ion is larger than a neutral oxygen atom. And this is just because of effective nuclear charge. The cations, there's less shielding because there's one less electron, and so we have a greater effective nuclear charge on the remaining electrons, and they get pulled in closer. So likewise over here, when we add electrons, we increase the repulsion, or the shielding, same thing, the shielding, and so now there's less effective nuclear charge felt by the outer electrons, and they expand out, become bigger. So we can predict the relative sizes of different species if, and this is a big if, they are in what we call an isoelectronic series. Isoelectronic means they have the same number of electrons as each other. For example, if you look at these species right here, the barium with a +2 charge. So if we look down here, neutral barium has 56 protons, that's its atomic number, and 56 electrons. The +2 ion loses 2 electrons, so it has 54. The cesium ion, +1 charge, starts out with 55 electrons. When it loses that 1 electron, it now has also 54. Xenon has 54 electrons. Iodide gains 1. It starts out with 53 when it's neutral, gains 1, has 54. Likewise, the telluride ion has 54 electrons, not valence electrons. So these all have the same number of electrons as each other, and that means that they are an isoelectronic series. And what we can say about an isoelectronic series is that the more protons there are in the nucleus, the smaller the size of that species. And again, it's because the more protons there are in the nucleus, the greater the effective nuclear charge, particularly because there's the same number of electrons. So barium with a +2 charge has 56 protons, cesium has 55, xenon 54, iodine 53, thorium 52. And so barium ion is the smallest, telluride ion is the largest in this isoelectronic series. So now, those are ionic bonds. Let's talk about covalent bonds. Covalent bond, the reason that covalent bonds is the same basic reason, the reason that they form is the same basic reason as ionic bonds, and that is that they do so in order to lower their energy. But here, it ends up that the electrons aren't removed or gained, more or less. We'll fudge that a little bit later. So if we start out with a real simple example, the hydrogen molecule, H2. If we look at this graph right here, if we start out with 2 separate hydrogen atoms far away from each other, the energy of this system be 0, call it 0. Now as we bring these 2 atoms together, so remember a hydrogen atom has 1 proton, 1 electron. As we bring them together, what happens is those electrons on one atom start to feel the positive charge in the nucleus of the other, and vice versa. And that lowers the energy of the system. Coulomb's law, like I just showed you a few minutes ago, the energy of interaction is negative, and that's lower. And as we bring these guys closer and closer together, those electrons get closer and closer to the opposite nucleus, and the energy of the system gets lower and lower and lower and lower until we reach a minimum. Once we get down here, guys, then we've gone so far, we've pushed those atoms so close together that now the 2 nuclei, the positive charges on each nucleus, they start to see and feel the effect of each other, and now that's repulsion. That's still Coulomb's law, it's just that there's two positive charges, so the energy of interaction is positive, pushes them apart, and so the energy starts going up and up and up and up, and it asymptotically approaches infinity. Asymptotically approaches zero distance because they cannot be in the same place. They can never be in the same place. So, what we can say is this: the distance at which we minimize get the most negative energy for the interaction between these two atoms is going to be the average bond length, the distance between the two nuclei. Now, in real life, well, this is real life, but what happens is it doesn't just sit there at the bottom of this well, but there's some energy in this molecule, and those atoms, the two hydrogen atoms or whatever they are vibrating back and forth like they're attached by a spring. But they oscillate about this distance, and so the average distance is going to be this right here. It ends up for hydrogen, it looks like it's 0.74 picometers. Another thing about covalent bonds is it always takes energy to break them, and when you form them, energy is always released because we end up at a lower energy. And the energy it takes to break a bond is exactly the same magnitude but opposite sign of the energy that's released when the bond forms. So if we take a hydrogen molecule, break it apart into two hydrogen atoms, we have to put in 436 kilojoules per mole of hydrogen. And if we take two hydrogen atoms and bring them together and form the hydrogen molecule, we release 436 kilojoules of energy per mole of hydrogen that we form. The next topic is electronegativity, and this is a definition. It's a strength with which an atom attracts electrons in a bond towards itself. So you have two atoms attached to each other, and there's basically this tug-of-war, guys, going on. Each atom on each side of that bond is trying to attract the electrons that are in that bond towards itself. And we have this scale. These numbers here are the electronegativities of the elements, and the higher this number, the stronger that atom attracts electrons towards itself. So if you have two different elements that are bonded to each other, it's an uneven pull. One atom is going to be more electronegative than the other, and so what happens is it pulls the electrons in that bond towards itself more strongly than the other one does, and the electrons get shifted towards the more electronegative element. Now, it's going to be really useful to know these numbers. I only ask that you memorize from hydrogen through chlorine. So hydrogen, lithium, beryllium, boron, all the way through chlorine. There's a real easy pattern here. So, well, hydrogen is just kind of weird, it's off by itself. It's 2.1, just kind of memorize it. But this first row has a really nice pattern. If you start out with 1, 1.0, it just goes up 0.5 every element you go over. 1, 1.5, 2, 2.5, 3, 3.54. Then, when we get to sodium, okay, it starts with 0.9, a little bit less than this, and it goes up 0.3 to 1.2, then another 0.3 to 1.5, another 0.3 to 1.8, another 0.3 to 2.1, and the last two go up 0.4 and 0.5. So memorize those numbers, put them on your card. It's going to be really useful for you guys to know. Remember, the higher the electronegativity, the stronger that element pulls electrons towards itself in a bond. Now, there's different ways of calculating these numbers. The numbers I just showed you are called the Pauling, from Linus Pauling, electronegativities. There are other ways of calculating them, but here's what he did. Here's how he calculated them. And these are the numbers we use, so this is just so that you know where those numbers came from. He said, all right, he expects if you have hydrogen attached to some other element, let's say, the bond energy, okay, the energy it takes to break those two atoms apart from each other, to break that bond, should be, he expects, the average of the hydrogen bond energy and whatever X is, XX bond energy. So add those two bond energies up. Remember, bond energy, the amount of energy it takes to break the bonds, and divide by 2. That's what he expected. But when we measure, we can measure these things, okay? So when we measure these things, we get an actual bond energy, and it's almost always different than what's expected. The difference between the expected bond energy from this and the actual measured bond energy is the delta. Okay? And it ends up that the bigger the difference in electronegativity between those two atoms, hydrogen and X, or it could be any two elements really, the bigger the delta is. So in other words, electronegativity, the difference, not just electronegativity, but the difference in electronegativity between the two elements that are bonded to each other has a big effect on how strong that bond is. Now, so we're going to classify bonds as ionic and covalent are going to be either pure covalent or polar covalent. But the first thing I want to get across to you guys is that this is not a hard and fast bright line. It's really a lot of gray area, right? So first of all, what we're going to say, so here's some numbers and these are what we're going to use. If the difference in electronegativity, so again, when I say difference in electronegativity, I mean the electronegativity of the more electronegative element minus the electronegativity of the less electronegative element from that table that I showed you a few minutes ago. If that difference is less than or equal to 0.4, we're going to say, well, that's not a big enough difference in electronegativity for those electrons in that bond to be shifted more one way than the other. So it's basically evenly distributed, and that's just a pure covalent bond. But if the difference in electronegativity between the two elements in that bond is bigger than 0.4 but less than 1.9, we're going to name that bond a polar covalent bond. And what that means is that it's still a covalent bond, it's not ionic yet, but the electrons are shifted enough towards the more electronegative element so that we actually have a negative region on the more electronegative element and a positive region on the less electronegative element. Now, once we get a difference in electronegativity, 1.9 or bigger, then we start calling that an ionic bond. And in an ionic bond, the only difference now is that the difference in electronegativity is so big that the more electronegative element is basically strong enough to remove the electrons from the other element, and we have a cation and an anion. Now, it's not quite that straightforward. It's a spectrum. There is no such thing as an absolutely pure ionic bond. There is no ionic compound where the electrons are entirely removed from an atom and on the other. There's some covalent character to every bond. It's just we make this line right here. And you know, there's always, you know, as long as its difference is bigger than 0.4, then there's some, you know, ionic character, negative and positive part to the bond. But these are the numbers we're going to use to generally to categorize bonds. So you should know them. So if the difference in electronegativity is big enough, then, like I was trying to explain a minute ago, the electrons in that bond, we call that the electron cloud, is shifted more towards the more electronegative element and away from the less electronegative element. For example, in hydrogen fluoride, fluorine's electronegativity is 4.0, hydrogen's 2.1. The difference is 1.9. Yeah, sure, we call this an ionic bond, but remember, it's not a bright line. And an ionic bond is really just a very polar covalent bond. And so there's a couple ways we have of showing this, and that's one thing I'm trying to show here. And two ways are actually in this picture right here. We draw this arrow towards the more electronegative element with the hatch on the other end. The hatch is on the end where there's a slight positive charge because that's the less electronegative element. And the arrow points towards the more electronegative element where the partial negative charge is going to be. We can also put these little deltas, delta plus towards the positive side, delta minus towards the negative side. These are deltas, they mean partials. It means it's not a full-blown positive or negative charge, but it's somewhat less. This picture over here comes from actually a computer program that basically uses numerical analysis to approximate the solutions to Schrodinger's equation and solves Schrodinger's equation and calculates the electron distribution in a molecule. And it draws this picture. It's this really cool program called Spartan. And in these pictures, the greater the electron density, the more the electron cloud there is, the more negative charge there is, the more red it becomes. And the less electron density there is, the more positive region there is, becomes more blue. So this is showing this sort of distribution of charge. This is called an electrostatic potential map, if you want to know. But when we do have this situation where we have a big enough difference in electronegativity so that there's a negative region and a positive region, we say that that molecule, or that bond, if it's just a bond, is said to be polar, or another way of saying that is that it has a dipole moment. Two poles, like on your car battery, plus and minus. Alright, so now Lewis structures. You may have seen how to draw these before, but we're going to go through it again. First of all, this is an example of a Lewis structure. And what Lewis structures tell you is they tell you how the atoms are connected in a compound. They tell you the order of attachment. Like this Lewis structure tells us that this carbon has 3 hydrogens attached to it. It's attached to another carbon, which has 2 oxygens attached to it, which has a hydrogen. It tells you what kind of bonds they are. These are single bonds. This is a double bond. And this is not supposed to be there. That's one too many pairs. These dots are non-bonding electrons. They're electrons that are valence electrons, but not involved in a bond. And two of these electrons together is called a lone pair. Each of these lines represents 2 electrons. So this double bond here, there's actually 4 electrons in it. It ends up, we're going to see a little bit later in this module, that knowing the Lewis structure helps us predict the actual 3-dimensional shape of a molecule, which is pretty cool. Alright, so what follows here, guys, is a step-by-step procedure for drawing Lewis structures. Get the steps down and make sure you don't skip any, because that's where you get in trouble. Alright, and by the way, if you get this first step wrong, you have no chance whatsoever of getting the right structure, so double check this first step. All you have to do here is count up the number of valence electrons in the molecule. So you know how many valence electrons each atom has. You can look at the periodic table, and those on my periodic table, the red numbers with A's after them tell you. But count up all the valence electrons, and if there's a negative charge on that molecule, for every negative charge, add 1 electron. If there's a positive charge, for every positive charge, subtract an electron. So we're going to use the sulfate polyatomic ion as our example as we go through this procedure. So sulfate is SO4 2-, so step 1 says count up the valence electrons. Sulfur has 6 valence electrons. There's 4 oxygens, so 4 times 6 valence electrons for each oxygen, plus the 2 negatives says we have to add 2 more, so we get 32 valence electrons. Again, guys, I really can't emphasize how important it is to get this step right. If you get this wrong, it's never going to work out. All right, step 2, arrange the atoms in the compound. This means, okay, so you're going to pick one, put it in the middle, and put the other ones around it. We'll talk about hydrocarbons a little bit, and then there's a few other things we have to think about. But for this is what we do. And so, which one goes in the center? Usually, it's the least electronegative. Sulfur is less electronegative than oxygen, so we'll start it in the middle. At the end, in step 5, we'll check that and see if there's maybe a better way to do it. But for now, put the less electronegative element in the middle. However, if you have hydrogen in there, because hydrogen can only form 1 bond, it can never be in the middle, so it's always on the outside. So, step 2, arrange the elements. I put sulfur in the middle, 4 oxygens around it. It does. Distribute them pretty, evenly. There's no one set way. I guess technically it would be wrong to maybe put all 4 oxygens on top, but that would just be ugly, right? So do it symmetrically. All right, step number 3: connect the outer atoms to the central atom with single bonds. So draw a line from each of the outer atoms to the center atom, and each of these is a single bond, and it has 2 electrons in it. And those 2 electrons are some of those valence electrons that we counted up in the beginning. So every bond that we drew, we subtract 2 valence electrons from our total. So we drew 4 bonds, that's 8 valence electrons. We started with 32, we counted them up. 32 minus 8 is 24 valence electrons left. That's where we are at now. That's step number 3. Step number 4, satisfy the octet rule for the outer atoms. And every time we add an electron, subtract 1 of that electron from our total. So let's do that before we talk about this. So we had 4 oxygens, each with a single bond. Saw 2 electrons. The octet rule says oxygen wants to be like neon, which has 8 valence electrons, so it needed 6 more. So we put 3 lone pairs on each oxygen atom. That's 6, 12, 18, 24 electrons. We've used them all up, don't have any electrons left. If we did, what you do at that point is you put them on the central atom, period. No questions, nothing else. Any remaining electrons after the octet rule is satisfied for all the outer atoms, put any remaining electrons, if you have them, on the central atom. On the other hand, if you run out of electrons before you've satisfied the octet rule, usually for the central atom, you're going to want to make a double or a triple bond. And we're going to actually do that for a slightly different reason in a few minutes, so I'll show you that. Actually, just a minute. Now, this step 5 is important because you're not done. Okay, so this ends up not being the correct Lewis structure for the sulfate polyatomic ion. Now we still have to calculate the formal charges. Okay, so first of all, how do you do that? All you do is you take the number of valence electrons for the neutral element, from reading the periodic table, minus the number of lines touching that atom in the structure, minus the number of dots on that atom in the structure. So let's do that first. So in this structure right here, sulfate polyatomic ion, each of the oxygens, a neutral oxygen atom has 6 valence electrons, minus 1 line, minus 6, 2, 4, 6 dots is -1. So these are all the same. So the formal charge on each of these oxygens, guys, is -1. And sulfur also has 6 valence electrons, 1, 2, 3, 4 lines, 0 dots. So its formal charge is +2. All right. So couple of things. You always want to have the Lewis structure that has the smallest size, smallest magnitude formal charges. Also, that's this minimum formal charges here. Also, the formal charges aligned with electronegativity. What that means is, if you have a choice, you don't always have a choice, but if it's possible, you want the negative formal charge on the more electronegative element and the positive formal charge on the less electronegative element. Here, that's true. But this +2, don't really like that. So let's see if we can do better than that. Well, if we take 2 electrons on one of these oxygen atoms, let's say these 2 right here, and we turn them into a double bond on that atom over here, then now we've gotten sulfur's formal charge down to, it ends up calculate that'd be +1. And this oxygen will be 6 valence electrons minus 2 lines minus 4 dots is 0. That's better than -1. But we can do even better. We can do the same thing on, say, here, on this oxygen. Now, we could have picked any of these oxygens to do it. And I'll show you what that means in just a moment. But what about the octet rule? Well, sulfur now sees 2, 4, 6, 8, 10, 12 valence electrons. We violated the heck out of that octet rule. But you know what? So what? If you go back and look at that slide on exceptions to the octet rule, you'll see that any element in the 3rd row or lower can have an expanded octet. Sulfur's in the 3rd row or lower. It has an expanded octet. It's much better to get good formal charges than to try to get 8 valence electrons. Within reason. That's not a blanket statement. So now, if we calculate formal charges here, sulfur has 6 valence electrons minus 1, 2, 3, 4, 5, 6 lines, 0 dots is 0. 2 of these oxygens have 0 formal charges, these 2, and these 2 have -1s. It's for a total of -2. Now, if you remember, sulfate has a -2 charge. Here's something to remember. When you add up, this is important, so write it down. When you add up all of the formal charges in your structure, they must equal the total charge on the compound. If it's 0, then 0. If it's not 0, they have to add up to be, in this case, whatever it is, so in this case, -2. But this is a better Lewis structure than this for sulfate. By better, I mean it's more likely to represent the actual structure of that molecule, that compound. So now we're done. Now we have the Lewis structure. The last thing we have to do is, because it's an ion, this is only if it is an ion, you have to put it in brackets and put the charge outside of the brackets. And there we go. However, there's one thing left to talk about, and that is we pretty much randomly just picked this oxygen and this oxygen to take the electrons from and make the double bonds. We could have picked any two oxygens and be just as good, right? Well, when that's the case, that tells us that we have resonance forms. And resonance forms exist when there's more than one equally good way of distributing the electrons in a Lewis structure without changing how the atoms are attached. So resonance forms differ only in the way the electrons are distributed. Now it ends up with sulfate, we have 6 resonance forms. Right? We could have picked these two oxygens, these two, these two, these two, these two, or these two. When you're figuring out different resonance forms, one thing I do, is, especially with something like this where there's so many, I pick one, in this case it's a double bond, keep it constant and move the other one around. And then, so that's these 3 right here. It's always, this oxygen always has one of the double bonds. Then I take that double bond and I put it on another one, say this oxygen right here. Then I move the other double bond here and here. I don't go here because we already did that structure over here. And then, so that's here, and then I move the double bond once more here, and the only one we have left is down here. So, what does it mean to have resonance forms? Well, first of all, the real compound only has one structure, period. But what they tell you is that the real structure it's like an average. It's called a resonance hybrid of all of these structures. So what does that mean? It ends up that we have the ability to probe inside of these compounds and measure things like bond length and bond strength. And one thing that we know is that a double bond, as long as it's the same 2 atoms we're talking about on each side of the bond, a double bond is shorter and stronger than a single bond, and a triple bond, 3 lines, is shorter and stronger than a double bond. So these are all sulfur-oxygen bonds, so we can reach in here and probe these, and what we do not see, this is what we do not see, we do not see, even no matter how fast we do it, we use lasers to do this, and we can pulse these lasers way faster than electrons can move now. And we do not see at one point an oxygen-sulfur double bond, 2 oxygen-sulfur double bonds, and 2 oxygen-sulfur single bonds, longer, shorter, weaker, stronger. What we do see is 4 exactly identical bonds that are an average of the single and double bond lengths and strengths. So those are Lewis structures. You'll get plenty of practice drawing them. That's all there is to it.